Hi everyone, I am Dr. Kachane, and today I would like to present my paper to you. The topic is a performance evaluation of the IoT and MQTT protocol, based water level warning system. This paper includes two authors. I am the first author, and the second one is Dr. Chanipa Sonklin. The outline of this paper includes an introduction, method, results, and discussion. The final part is the conclusion and future work. So let's start with the introduction. The IoT plays a vital role in the connectivity of sensor networks because the IoT allows sensors such as actuators, ultrasonic sensors, and humidity sensors to communicate and exchange data with each other. This leads to various smart systems, including smart homes, smart vehicles, smart farms, and etc. With the rapid movement of this device communication, smart systems require protocol to support them in terms of availability, reliability, low latency, and high throughput. Message queue telemetry transport or MQTT is one of the most popular protocols in IoT MQTT-based applications. MQTT is the protocol in IoT based on the publish-subscribe communication to send data from a publisher to a subscriber through a broker. It also provides lightweight IoT messaging, simple implementation, open standards, reliability, and system efficiency, including memory, CPU, and network resources. MQTT has been designed to support various communication patterns, such as one-to-one and many-to-many communication. Several studies have been done on the MQTT protocol because it is easy to implement and deploy. MQTT protocol also provides real-time and reliable communication between publisher and a subscriber. For instance, the authors from Sonklin and others propose a framework based on publish-subscribe communication using the MQTT protocol to evaluate the framework's performance, such as latency and reliability. Extensive experiments were conducted. They claim that the reliability of their system was more than 96%, while the latency was less than 300 milliseconds. However, few studies have been conducted to convert the overall performance metrics. Therefore, this paper aims to develop the water level warning system prototype using the MQTT protocol and then evaluate the performance of the proposed system with different metrics, including latency, throughput, packet loss rate, packet delivery ratio, availability, and accuracy by simulation experiments. The analysis is performed to discuss the experimental results. The main contribution of this paper is performance evaluation of the proposed system through simulation experiments and their analysis to investigate the optimal parameter values and their correlation with different data transmission rates to support IoT applications. This is essential to provide practical guidance for the future design of IoT applications. The next section is method. The performance of the proposed water level warning system is evaluated through simulation and experimental analysis. Several hardware and software tools are used to develop and evaluate the proposed system. This is implemented using Node-RED as a subscriber Node microcontroller unit based on ESP32, Node MCU as a publisher, the MQTT broker as a broker, and ultrasonic sensor to send data. The ultrasonic sensor is a low-cost sensor and can be performed well under extensive conditions, such as temperature and pressure. In this study, we used an ultrasonic sensor to measure the water level and send data to ESP32 node MCU, which is a system-on-chip microcontroller with integrated Wi-Fi and Bluetooth-enabled development board based on the ESP32 microcontroller. It has been widely used in IoT systems due to its affordability, energy efficiency, and powerful computing capabilities. Node MCU need to be connected to Wi-Fi modem. Once connected, Node MCU could send a sensor-generated data to the MQTT broker over the internet. After the server processes the data, subscribers can access it through a create application. Our system uses Node-RED, a virtual programming tool, as a subscriber and create an application. This is because Node-RED allows users to wire together device, API, and online service to develop applications and automate workflows. Particularly, this tool is popular in IoT implementations where it is used to connect and control IoT devices, collect, analyze sensor data, and create IoT applications. In the process of collecting data, ultra- ultrasonic sensor is used to collect water level data from water tank. After that, data is transferred from Node MCU via the MQTT broker to analyze the performance metrics of the proposed system prototype. For the performance test parameter, various parameters are used to evaluate the performance of the proposed system prototype, such as latency, throughput, packet loss rate, availability, and sensor accuracy. In the next section, I would like to talk about the results and discussion. The experiments are conducted to illustrate the performance of the proposed water level warning system prototype using IoT protocol with various parameters described in the previous section. Then, the results are analyzed and discussed to find the optimal parameter values and their correlation with different data transmission rates to support IoT applications. To evaluate the performance of proposed system prototype in terms of latency, throughput, packet loss rate, packet delivery ratio, reliability, and availability. Four sets of experiments are designed. The MQTT protocol is used to demonstrate message transfer with different data transmission rates. In the experiment, Node-RED as a subscriber is set up on a personal computer with a wide connection while Node MCU as a publisher and the MQTT broker as a broker are set up on the same laptop with Wi-Fi connection. The MQTT broker is installed to run as a middleware of the publish-subscribe communication with QoS level 0. Data transmission rates are 1 Hz, 2 Hz, 5 Hz, and 10 Hz. In this study, Hz represents the frequency at which messages are sent per second. Every experiment is run for 60 seconds and repeat 30 times. The Wireshark software is used in the experiments to measure the system performance. The detail of each set of experiments and the results are discussed in the following subtopic. Let's start with the experiment 1, latency of message exchange over MQTT. The measured latency includes the latency between Node MCU and MQTT broker and Node-RED, and Node MCU and Node-RED. The average message transmission for three measured latencies at various data transmission rates. The results show that the latency increased when the data transmission rate increased from 1 Hz to 10 Hz. Transmitting data at a high data rate enable data to be published quickly, similarly to the work of Canada and others. The authors conclude that an increase in data transmission rate result in a greater latency. However, our latency result outperform the system prototype of Cardano and others in the message transmission rate at 1 Hz, 2 Hz, and 5 Hz. This clear visualization illustrates the direct impact of data transmission rates on latency, emphasizing the need for higher transmission rates for enhanced efficiency. For the experiment 2, throughput of message exchange over MQTT. This experiment aims to investigate how throughput is affected by data transmission rate. The results show that throughput performs well when transmitting message from Node MCU to MQTT broker and from the MQTT broker to the subscriber at the 10% data transmission rate. The result also demonstrate that higher data transmission rates leads to an increase in throughput. For experiment 3, our variability PDR and PLR. This experiment investigates how data transmission rates affect the variability PDR and PLR of message transmitted from the publisher to the subscriber. It can be seen from the results that when the data transmission rate increased from 1 Hz to 10 Hz, PLR increased, whereas variability and PDR increased. As the data transmission rates increase, the number of packets transmitted per second increase, lead to more packet loss in the work of Perdana and others. Furthermore, more packets are being dropped because of the MQTT QoS level 0 message transmission method, which does not guarantee that the subscriber will receive the message. Consequently, this can lead to packet loss and reduced availability and PDR. However, the results demonstrate that availability and PDR have a value of up to 97.8% with only 2.2% PLR at 1 Hz data transmission rate. Therefore, the data transmission rates affect the variability, PDR, and PLR. And the last experiment is sensor accuracy. This experiment investigates how accuracy the ultrasonic sensor is when transmitting message from node MCU to subscriber at different data transmission rates, including 1 Hz to 10 Hz. The results demonstrate that IMSE value increase when the data transmission rate increase. The lower RMSE value imply that the sensor reading are close to true values, indicating more accuracy performance. The sensor transmitting message at the 1 Hz data transmission rate has the best accuracy with an IMSE value equal to 0.71 and has a higher accuracy of 82.77% compared to the others. It is concluded that data transmission rate affects the sensor accuracy. The last section of this paper is conclusion and future work. In this paper, we have designed and assessed an IoT-based water level warning system employing the MQTT protocol, demonstrating marked enhancement in key performance metrics, including latency, throughput, packet loss rate, packet delivery ratio, availability, and accuracy with different data transmission rate. The experimental results have shown that the proposed prototype achieved up to 98% availability and PGR with minimal PLR. The experimental findings also reveal that increasing data transmission rates enhance throughput while decreasing latency, availability, PEDR, and sensor accuracy. In other words, higher data transmission rates lead to higher throughput and latency performance, with lower performance in terms of availability, PDR, and sensor accuracy. This highlights the critical importance of optimizing these parameters for the efficiency of the IoT implementations, especially substantial potential solution for real-time flood monitoring and response applications. Therefore, this outcome significantly advanced the field of IoT-based environmental monitoring, providing valuable insight for the development of smart city infrastructure and disaster management strategies. In the future works, we will focus on the integrating additional sensor type and evaluating the scalability of the system with more extensive and complex environments. Furthermore, assessing the system performance under diverse environmental conditions and varying data loads will be essential for validating its robustness and applicability across different scenarios. This is the end of my presentation. Thank you.